Hello dear students, in today's lecture we will try to understand more aspects related to the MHD approximation. We will derive the MHD equations. In the last lecture we have seen when is MHD approximation valid, what are the conditions under which we can combine the equations pertaining to electron and ion and get a simple equation or get a unified expression for various laws of conservation of, let us say, for example, conservation of mass, energy, momentum, etc. Right. So, in the last lecture, we have already defined what is the mass velocity, what is the total current density, what is the total pressure, etc. So, we have seen the total mass density or rho m as NEME plus NI MI, and we have also defined what is, we will not write down the expressions again, we have defined what is the total current density, then we have defined a quantity um, which is basically the mass velocity, and we have also defined what is the total pressure because of the electron and ion fluids separately. So, in today's class we will first obtain the combined equation of continuity and or for example conservation, we will obtain two equations, one for the conservation of charge, another for the conservation of mass. Okay. So, we will call it as combined equation of continuity. Okay. So, let us start from what we know already, which is dou Ne by dou t plus del dot Ne ue is equals to 0. So, Ne is the number of electrons per unit volume. The rate at which number of electrons changes will be equal to the negative of the divergence of Ne times ue. Okay. So, this is for electrons obviously, and we can also write a similar expression for the ions, which is dou Ni by dou t plus del dot Ni ui is equals to 0. Let us say we call this equation as equation number 2. Now, the idea of MHD is that we will no longer treat plasma as a two fluid, one electron fluid or ion fluid. We will simply treat it as a combined single fluid. Okay. So, in order to combine these two expressions, we will multiply the equation number 1 with, let us say, QE, and the equation number 2 with QI. What is QE? QE is the charge of electron, QI is the charge of ion. After multiplying these equations, we will add both of them. Okay. So, we will get something like this, which is QE dou Ne by dou t plus del dot QE Ne ue plus QI dou Ni by dou t plus del dot Ni QI ui is equals to 0. Right. So, we can write it as dou by dou t of QE Ne plus QI Ni, which becomes the total charge, plus divergence of QE Ne ue plus ui QI Ni is equals to 0. Nothing to worry about. It is just a simple addition of both the equations 1 and 2. So, this whatever that appears within this bracket is the total charge density. Ne is the number of electrons per unit volume, QE is the charge of a single electron. So total charge contained in this volume becomes QE, the negative charge, and the positive charge. Okay. So we can substitute this as dou by dou t of rho plus del dot, what is it? NeV, which is appearing just like the current density, which we know that J is equals to NeVd. We are familiar with this current density term. So whatever that appears, this becomes the current density for electron, and this becomes the current density for the ion. So we can write del dot J is equals to 0. Right. So what is this? The rate of change of charge density plus divergence of current density will be equal to 0. That is the meaning of this particular expression. Right. So what type of conservation is this equation talking about? This equation is talking about charge conservation, which means if there are to be any changes in the charge density, these changes are equally represented by the opposite changes in the current density. Okay. So this is the charge conservation. We can also obtain mass conservation starting from the equations 1 and 2 itself, but rather this time instead of multiplying with respective charges of electrons and ions, we can multiply equation number 1 and 2 with mass of electron and mass of ion, and then subsequently add these two equations. We should be getting the same type of equation. So I'll write it as dou by dou t of NeMe plus del dot NeMe UE is equals to 0. Similarly, after multiplying this equation number 2 with the mass of ion, which will be Ni Qi plus del dot Ni. Yeah, I made a simple mistake. It should be, there is no charge in this. Ni Mi and Ui is equals to 0. What do we do now? We add these two equations and write it as dou over dou t of NeMe plus is equals to 0. Right. So what is this? This is the total mass density. N is the number per unit volume, which is 1 by V. Me is the mass by volume, which is density, right? So we can rewrite this expression as dou over dou t of rho e plus rho I del dot rho e ue plus rho I ui is equals to 0. So we can define the fluid mass velocity as is equals to NeMe ue plus Ni Mi ui divided by kind of like normalizing with respect to the total density, okay, which is nothing but Ne right. So, we can use this. So, this can be, all of this can be um, right. So, this term which is appearing in the numerator is what we have here, this term. So, instead of this, a suitable substitution can be made in terms of mass velocity times the total mass density. So, then we can write dou by dou over dou t of rho m, total mass density, plus del dot um rho m is equals to 0. Okay. So, this is, what is this equation telling? Equation is the rate at which density is changing with respect to time is equal to the negative of the divergence of velocity times the density. So, here there are no charges. So, the conservation that this equation is representing is basically mass conservation. Okay. So, if you go back, the earlier equation is telling you the charge conservation, and this equation is just giving me the equation of mass conservation, right. So, we have continuity equation in terms of for the charge, for the mass as well, right. And what else we have? We have in which governing equation should we require, right. So, we will require an equation of motion which is just of the form F is equals to ma. Okay. We have obtained the continuity equation. Let us see how we can get the equation of motion for the bulk plasma or the single fluid plasma. So, which is now the equation of motion for the bulk Okay. So, we know very well that if we are talking about a fluid, we should always take into account the total derivative, how the velocity is changing with respect to time as the fluid is moving from one point to another point. Then the rate of change of this velocity should always be equal to the sum of all the forces which are responsible for the movement of this fluid from one point to another point. That is in total the essence of the second law of motion, right. So, the equation of motion for the single fluid plasma can be obtained if we add the momentum equations of both electron and ion. First, we will write down the electron momentum equation and the ion momentum equation, and then we will try to add them up. Okay. So, which will me ne dou ue by dou t plus right. I could have just kept me ne outside the bracket. It would have been easy to identify the total derivative which is appearing as a sum of this and this. Okay, the partial derivative plus the advection term. Nonetheless, so we have right. Let us say we call this equation now as equation number 1. So, the rate of change of velocity and the advection is equal to the sum of the electrodynamic forces and the kinetic forces. We can also write a similar expression for the ions mi ni dou ui by dou t plus mi ni ui dot del times ui is minus del pi plus qi ni times e plus ui cross b. Fine. So, this is equation number 2. What do? We just combine both the equations. Simple algebra will allow you to add both the terms. So, I will write them by skipping one algebraic step. So, dou by dou t of me ne ue plus mi ni ui equals to minus fine. So, I think what I have missed in between is just I have neglected the advection term, assuming that it will be very small in comparison to the variation with respect to time, or the velocity is not changing much with respect to the position. Okay. So, using this is what we know already. This is using what we know, we can write dou over dou t of times me plus mi is equals to minus plus okay. So, this is the current density, right? I just brought the current density as Je and Ji. A sum of these is now being referred as J. Right. So, this equation looks very familiar to what we know already. Okay. So, summarizing this, we can write the final idealized MHD equation or equation of motion for a single fluid plasma is Ne me plus ni mi mass velocity dou t Okay, so this is the idealized MHD equation for a single fluid plasma or the equation of motion. So, the single fluid model or the MHD approximation takes the plasma as a conducting fluid which is completely ionized. We have already removed the provision of having neutrals, and the final fluid equation describes the variation of current density with respect to time. So, the final equation, basically the Ohm's law, we will derive the equation of how the current density variations with respect to time can be accounted in terms of other parameters. Okay, so we can use the equation, but how can we get that equation? We have the equation number 1 and 2 earlier, momentum equations 1 and 2. So we can start from this equation. Let us write a single equation for this, okay, instead of writing two equations every now and then. Let's say mi ni dou ui by dou t. Okay, I can be confused with ion, right? So instead of writing I'll use a subscript j, mj nj dou uj by dou t plus uj dot del times uj is equals to minus del p plus qj nj times E plus uj cross b. What is this equation? So j is a subscript which can go from, let's say, 1 to 2. 1 can be your electron and 2 can be an ion. So this equation is written for both the particles, electron and ion, just with a subscript. And looking at each term, we have the pressure gradient force which is appearing on the right hand side and the Lorentz force. So these two forces are only responsible for the rate of change of velocity with respect to time. Which velocity? It can either be the velocity of electron or the ion. Now this equation can be written or can be used to obtain the dJ by dt, the rate of change of current density. How do we get it? So this equation, we can multiply this equation with once with QE divided by ME. You are writing the electron equation and multiplying that equation with this, and then you multiply the same equation for ion with QI by MI and add both of them. Okay, so if you do that, I'll write the final forms, which will be like QE by ME times QE NE dou UE by dou T plus UE dot del times UE is equals to minus del PE plus QE NE times E plus UE cross B, right, plus QI by MI multiplying QI NI I hope you are following what I'm writing here. It's very simple. I'm just using the equation that I have used to obtain the equation of motion. Okay. Right. So these two equations are supposed to be added. Now simple, what we get? We get a larger equation. So dou by dou t of QE NE UE plus QI NI UI is equals to minus QE by ME del PE minus QI by mi del pi, fine, plus ne qe square divided by me plus ni qi square divided by mi. This entire term being multiplied with E plus ne qe square divided by me multiplied by ue plus ni qi square multiplied divided by mi times ui cross b. Okay. So, what has been neglected? It is only the advection term which has been neglected, right. Now, let us say we assume the plasma to be electrically neutral, which means Qi Ni will be in magnitude be equal to Qe Ne, which means the total negative charge will be equal to the total positive charge. Okay, just a moment. Okay. So, with this total charge being, the total charge in principle should be 0, right, and we know the expression for the current density and for the mass velocity. So, whatever appears here is nothing but the current density. So, we can write the final expression as the rate of change of current density dJ by dt, or if you want to carry the same notation, T will be equal to minus QE by EME times del PE minus QI by MI del PI plus NEQE square by ME plus okay. So, this is what we get. So, the rate of change, so if you equate these two, if we assume the total pressure gradient to be equal to the sum of these two, then we can combine these two expressions and write a single term, and this one also can be reduced, and this one, these three terms will be equal to the rate of change of current density. So, this equation is called as the final fluid equation. Rate of change of current density. Basically, the magnetohydrodynamics couples the Maxwell equations with the hydrodynamics to describe the behavior of highly conducting fluids such as plasmas. Okay, so this is where we will stop.